Alrighty, today we're going to look at parent functions, and you have this graphic organizer part 1. Part 2 will come like next 6 weeks. It won't be the next lesson. We're going to look at them at a set at a time. Parent functions are not new to you. All of the parent functions that are in this organizer are ones that you should already be able to recognize and know some of the characteristics of. So if I showed you a picture of a cubic, you should be able to tell me it's a cubic and know some stuff about it. So I am going to get you started on this. We're going to talk about a few key features here, and then you're actually going to fill out most of this on your own. All right. So parent functions. We have what's called a function family. Right? Function family is a group of functions with similar characteristics. The parent function is the simplest of the functions in the family. You must be able to recognize each of these functions along with their characteristics. Okay, this is an absolute must. This doesn't go away. It's going to continue on through calculus and however far you go with that, but parent functions and being able to do their transformations are super duper important. All right, so we're going to start with the most basic we have, which is the parent function of a linear, and you've learned about lines long time ago. So our parent function, the equation itself, is f of x equals x. Okay, that's it. That's the simplest line you have. And along with these parent functions, you're going to have anchor points that you're going to need to know. They're pretty easy to figure out, and it's not a matter of memorization. It's just thinking about what makes sense with the function. So our anchor points here are 0, 0, 1, 1, and negative 1, negative 1. Those are our 3 points that are going to help us do our transformations. So when we get to the transformations, we are not substituting in numbers to get a t-chart. We are using the anchor points and understanding how the graph is moving around on the coordinate plane. So those anchor points are what become key for us. So I have this little t-chart over here for you to fill in. Now, if you don't really like using Cami, I'm still not trying to make you force you, but I'm trying to encourage you because the more I use it, the more I understand it and the better I like it. So if that's kind of too small for you to write in, you can pinch and zoom just like you would on your cell phone and make this bigger. Well, when I make it bigger, I'm on a 2 right now for my width. I'm going to change it to 1 or it's going to be way too fat. And I'm going to have they're negative 1, 0, 0, and 1, 1. And then I can zoom back out, and then it looks much better than if I'd have tried to write it really small. Okay, so those are my anchor points, and move back to a 2. And you'll either have 3 or 5 depending on the function. In this case, it's 3. We don't need any more than that. All right, so our domain, well, it's all real numbers, so we're using interval notation. So this is going to be negative infinity to infinity. Our range, same thing, negative infinity to infinity. Okay, and those are open because you never include your infinities. So then our x-intercepts, where does it cross the x-axis? And since this says intercepts, it's not a set, it's an ordered pair. So this would be 0, 0. And then my y-intercept is also 0, 0. Okay. Extrema, that is my, I meant to change this. I meant to change that to critical points because extrema is just relative max and min and absolute max and min, but I wanted to include point of inflection. So point of inflection is not an extrema, but I really meant to put critical points here. So that we're going to pretend like that says critical points. I don't have any here. I don't have a max. I don't have a min because those have to be values. And these go to infinities, and infinity isn't a value. Okay, it's a concept, and it can really make your brain hurt when you get into discussions about infinity. So I have none. There's also not a point of inflection. Okay, increasing. Remember, that's talking about our y values. Our y values, starting out when x is at negative infinity, our y values increase forever. So our increasing interval is negative infinity to infinity. And the decreasing interval is none. Okay. So our end behavior. Remember, end behavior is as x approaches negative infinity, and this is the only time you go to the left for anything that you're trying to discuss. So as x approaches negative infinity, as it goes out here, probably shouldn't have actually written that on there. As x approaches negative infinity, f of x also approaches negative infinity. And then as x approaches infinity, f of x also approaches infinity. All right. Does it have any discontinuities? I don't see any discontinuities, so there is none. And then is it even or odd? Okay, so you should be able to tell by looking, but I want you to show me, because these will all be very easy to show. I want you to show me, that's one of the reasons you have the space down here, what it looks like algebraically. So to figure out if it's even or odd, I have to do f of negative x, and f of negative x equals negative x, and that is negative f of x, and that is what actually makes it odd. Okay. The space I put down here for you is for any little notes you need to make up for yourself or whatever. But I've figured all that out. Okay. Now, I'm not saying that you had it all memorized to begin with or anything, but things you should be able to understand from the graph. Okay. All right. So now let's move on to absolute value. So my absolute value parent function is f of x equals the absolute value of x. And then my anchor points here are these three right here that make the little v. So this is negative 1, 1, 0, 0, and 1, 1. Okay. You're going to fill in the rest because you should be able to explain all the rest of that from that function and understanding what you understand about it. Okay. I'm pretty much just going to go through, we're going to talk about the equations and the anchor points of these. All right, so my parent function here is going to be, for a quadratic, we should know quadratics pretty well, f of x equals x squared. So I have three of my anchor points are here, here, and here. But that can't be it because those are the same three for absolute value. So I actually need more on these, and this one I'm also going to have one here and one here. Okay. So I'm going to zoom in so I can write these, and maybe I can actually make them fit. If we need to extend that line, because I didn't make it long enough, I know I didn't. So my 5 points, there's 5 on this one. It's negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Okay, so those are my 5 anchor points. And I know somebody's going to ask, do I have to memorize them? It's not a matter of memorizing them. It's a matter of understanding how a quadratic works and being able to come with those 5 points. All right, so then you can do the domain, the range, and everything else on that. Okay, let's look at the cubic. So the cubic is at f of x equals x cubed, what a cubic looks like. And then we have 5 anchor points here also because these 3 are the first 3, but then that's the same as a line. So I need some more information. So these other 2 actually don't fit on here. So at 1, I'm at 1, and at 2, I would be at 8, and at negative 2, I'd be at negative 8. So I can't plot them on here, but we are going to write them down. Okay, so I need negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. Okay, so those are ones that you gotta know. Gotta know what goes along with this cubic here. I am going to fill in one more thing on this with you because I don't want this to be a source of confusion. Because again, I did intend for this to say critical points, and it says extrema instead. So I don't have any extrema on here again, but I do have a critical point. This point right here, that's where the wiggle is. That's where it changes its shape. So 0, 0 is an important point, and that is a point of inflection. And then again, you should be able to complete that. Square root function, f of x is equal to the square root of x. And here I only need 3 anchor points. So I have one here, and one here. So those end up being 0, 0, 1, 1, and 4, 2. One other thing I'm going to add on to this is the end behavior, just because this one's a little weird, and we'll talk about why it's weird. And right now, I guess, I was thinking it came second. So this doesn't approach infinity. Like, it stops right here. So there's no approaching infinity because there's no arrow over there. It ends at 0. So we say, instead of as x approaches negative infinity, because it doesn't when I'm going to the left, it hits 0 and it's done. So I say as x approaches 0, and not just that it approaches 0, but it's approaching 0 from the right side or the positive side. So I have a little tiny little plus up here. If it was approaching it from the left or from the negative side, I have a little tiny negative up there. And we'll talk about that more when we get to limits. But as x approaches 0 from the right, that's what that means, f of x approaches 0 also. And then, oops, I think I forgot to do a semicolon on the other one. It's fine now. Then as x approaches infinity, f of x, oh, shoot, no, just f of x approaches, and it's approaching infinity. I didn't make those lines long enough either. All right, so then the last one is the cube root, or the last one for now anyway. This is f of x equals the cube root of x. I have 5 anchor points here also because these are 3 important ones. Well, those 3 are the same 3 for linear and the same first 3 for cubic. So I got to have more. And again, these don't fit on here. So this would be, I'd be out here at 8, 2, and at negative 8, negative 2. So let's put those on here. So I'd have negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. Okay. Now, you should be able to fill in the rest of this based on your knowledge you already have of these concepts and with this graph right here. Okay, so get this part complete, and then we're going to look at the reference sheet. All right, so the reason we have to know our parent functions very well is because we're going to be transforming them all over the place, and we can't be struggling about what is this parent function even. Okay, so there are 2 main types. There's rigid and non-rigid transformations. So rigid is the change in position or orientation of a function. So that's translations and reflections, same kind of things you talked about in geometry. Non-rigid transformations distort the shape of a function by changing its size. So those are dilations. Okay, so let's look at what happens here. These, again, this is a total review from Algebra 2 and Algebra 1 as well. So a translation, that's just if I'm just going to take the function and move it up and down. So when you do that, all you're doing is adding to the end of the function. So to shift it down, we would have f of x minus d. Okay, and d is just a number, right? So if I have x squared minus 5, my x squared gets translated down 5 units. Up would be f of x plus d. Right? Then when I shift it left and right, when I have those sorts of translations, that's when we add or subtract from the x before it goes through the function. So this would be f of x plus c and f of x minus c. And remember that x lies. Okay, I'm going to say that a lot. X lies. So here, when we have f of x plus d, that means I'm adding, so I'm going up. Here, f of x plus c, well, the x lies, so even though this looks like it's going to the right, this is actually a translation to the left. And since, again, x lies, this is a translation to the right. Okay. When we reflect, so if I'm going to reflect in the x-axis, remember what we thought about is that if I'm going to take this and I'm going to reflect it in the x-axis, the x value stays the same, but the y value changes signs, right? Well, y value is f of x, so it's negative. Negative f of x, negative y. I'm changing the sign on y. When I reflect in the y-axis, I change the sign on x, so it's f of negative x. Right? My dilations, this is when we're multiplying. Okay, so we have compressions and stretches. So vertical, since it's vertical and your y-axis is vertical, then you are multiplying by y. Vertical is y. So it would look like a times f of x. And then there's a little clarification there. The absolute value of a has to be between 1 and 0. Because the reason it's the absolute value is because the sign is the reflection. So if it's a negative a, that negative takes care of the reflection. So all we care about is the absolute value of a. And if it's between 0 and 1, so if it's less than 1 when it's positive, like a fraction, not all fractions though, because 5/3 is not less than 1. But if it's a fractional unit less than 1, then it's going to be a compression. Okay, you squish it down. And then when I have a times f of x, also looks exactly the same, right? So we're multiplying by a. What's different is the value of a. If the absolute value of a is greater than 1, then it's a stretch. So if I have 4 times f of x, then that's going to stretch it by a factor of 4. Okay? So this says the function will compress, or stretch vertically. Remember, it's vertical because it's the y value here, by a factor of the absolute value of a. Now let's look at our horizontal dilations. Again, should totally be a review. So this time, since it's horizontal, we are multiplying by x. So that would be f of b times x. Okay, b is some number. And here, the absolute value of b, if the absolute value of b is greater than 1, so like if this was 3 times x, that's a compression. Because remember again, x lies. So it looks like it should be 3 times as big, but it's not. Okay? And then a stretch, we're going to have, again, it's just f of b times x. And then this time, the absolute value of b is less than 1, greater than 0. So it'll be like 1/2 or 2/3 or something like that. Basically, these two are opposite here. So here, the function will compress or stretch horizontally, because we're multiplying by x, by a factor of, not of b, because x lies. So instead of multiplying by b, we're really dividing by b. So when you talk about it as a factor, you're talking about multiplication. So this is the absolute value of 1 over b. So if this was 4x, like I said, okay, because b is greater than 1, so if it's 4x, then it would actually be stretched or compressed by a factor of 1/4. If this was 2/3, then it would actually stretch or compress by a factor of 3/2, and that's why it makes it the opposite there. Okay, so those are your basic concepts of your little review for transformations. And then it's on here, on these rules here. Basically, it says the same thing. I just wanted to talk through it. And I have it in function notation, then I also have it in coordinate notation, so you can think about what's happening. Remember the horizontal, if it's plus, you're going to the left. If it's minus, you're going to the right. Okay, and it's showing you what's happening over here. So I want to talk through something. Let's see. Let me give you this function here. So we're going to have f of x equals negative 1/2, and I'm just throwing everything in there at once. We're going to start off a little smaller than this, but we'll talk about what each one of these pieces does. 3 times x minus 2 squared minus 5. Okay, so I need to be able to look at this and know what my parent function is. Okay, my parent function here, it's a quadratic, so see how this is like would give me some x value that I'm going to square. So my parent function is f of x equals x squared. So when you're trying to decide if something's happening to x or happening to y, it's happening to x if it happens before you do whatever the function is. So, So whatever happens before you square it is happening to x. Whatever happens after you square it is happening to y. Okay? So That means here, this negative, you have to decide, does that affect x or y? Well, it's happening after I squared it, so it's affecting y. So when you have a negative f of x, or you're changing the sign on y, this would be a reflection in the x-axis. This 1/2 is a factor for y because it's happening after you square the x. So this 1/2 would be a vertical compression because it's less than 1. This 3 is happening before I square it, which means it's affecting x. So since I'm multiplying it by x, then this is going to be either a stretch or compression. But remember, x lies, so I'm not multiplying it by 3. I'm multiplying it by 1/3, which makes it a compression. This 2 is in here before I square it. Therefore, it affects the x. And when I subtract from x, x lies, so that means I'm actually going to the right 2 units. And then this 5 is happening after I square it, so it affects y, which means I'm going to shift down 5 units. Okay? Now, again, we're going to go through that and review that a little slower. The activity that I have for you in Delta Math, I wasn't really going to give you like an assignment with this, but I found something I really liked in Delta Math because it makes you play with it. Like you have to look at it and it tells you to change it into something. So you have to figure out if you're supposed to reflect it or if you're supposed to translate it left or right. And so I think you can discover a little stuff and maybe make some of those things make sense for you there. Okay, so get all that done. Be ready to start graphing like crazy next week.